a brief introduction on who's giving this talk. I've been working 20 years in the domain of active optics, and since 2007 I've been employed as staff in the European Space Agency. Almost immediately upon my entry in the agency, I started working on space lasers and space LIDARs. I became integrated in functional support for the development of the ALTER-ETSIT LIDAR, which is an instrument in Earth observation mission. And ever since I've been building and developing space LIDARs, not that much large size as like the ones we just saw, but more like the ones that will follow my representation, which are for imaging and range finding purposes. I have a couple of photos here. It's the one on the left. The bottom left, you see it's actually a school we had in European Space Agency for active optics, so we can teach the principles of LIDARs, and some of you can recognize yourselves in this school. And the photo on the right is a similar workshop we organized in a nice location in Milos Island 2018, where we actually had a very good meeting also discussing LIDAR activities. Can you see slide 3 now?
Yes.
Yes. Excellent. So a quick outline of my presentation. I will try to switch a little bit with respect to the title. I will start from the space LIDAR applications, which are quite a lot, as you will see. And then I will present you the typical architecture of a system, a LIDAR system, in particular, large size, which is used for the top 4 categories, which is topography, greenhouse, clouds, and winds. And then I will go on in differences of space LIDAR technologies with respect to ground systems, because you already saw some information about the ground system LIDARs, and you will hear in the next presentations also what are the requirements and the needs, but I will present what are the biggest issues we have when we try to take a system from the ground and put it into space. I will present the lessons learned both from our side, the European Space Agency, as well as some of the issues they had to face from NASA, and finish with the conclusions. So if we look at space applications for LIDARs, you see that there are quite some. Actually, they're not 1 or 2, but actually we have 8 distinct areas, domains, where we actually we can have these LIDARs. And then if you ask how many LIDARs we have flown and how many LIDARs we have operational, sadly, we don't have that many. It's a new technology for space. We have the first launch of LIDAR was actually, if you look at the table on the right, was with MOLA 1 from NASA in 1992, but it didn't switch on until much later because it had to fly to Mars. The first light from space was mission LIGHT, also from NASA, which was mounting a profiling LIDAR in a space shuttle, and they opened the space shuttle bay and they fired towards the Earth. They immediately discovered the big issues and troubles you face when you operate at the UV at 355, because it had a rapid energy deterioration due to contamination. But that was also a driver for them to develop new and simpler designs. And already mentioned in 2005, they launched Calypso with a Calliope instrument, which has been flying ever since and giving remarkable results. One of the drivers of this success was that the simplicity of the instrument, because it was not using the UV, and it was a simple 532 nanometer 1064 neodymium YAG main mode and second harmonic generation by KTP crystal. A simple example to how difficult it is to use more complex systems is that below Calliope, you see also another ESA NASA effort, which was the CATS, which was mounted, launched to the ISS and mounted the Kibo, Japanese part of the ISS, and it faced limited functionality. The UV failed immediately, and the HSRL also failed. So it's a typical example of how difficult it is to put very complex instruments in space. So if we start with the first category, you see topography, cryosphere, and biomass. I will start with an activity and a mission that I'm responsible for, not the mission, but the instrument. On the left side, you see we have this mission called HERA. It's an evolution of the AIM mission, which was cancelled. And our plan is to send an instrument, satellite, to the Didymos asteroid. On this mission, we have a micro LIDAR, which will be used for imaging and altimetry. A very interesting comment about this LIDAR is that originally it was one of the tentative scientific instruments, but that distance is from Earth. The uncertainty of the platform with respect to the asteroid was more than 500 meters. And that meant that the satellite could not get really close to the Didymos asteroids, and that was needed for scientific purposes. So in one of the meetings in OHB, which is the prime development of this mission, I told them that, by the way, you have this instrument, candidate instrument, which is for scientific purposes, but for if you prefer using it for AOCS, you can get 1 centimeter accuracies or 10 centimeter accuracies at the distances you are mentioning. And they were shocked, and immediately this became one of the main instruments of the mission, because it allows the mission to go as close as 100 meters to the asteroid. What you see here on the left side is that the preliminary breadboard was developed in 2017-18, and the follow-up continuation as the design as it is planned to be during PDR level. You see the left side of can you see my cursor? I hope you can see it. The left side of this instrument is the electronics box, which now you see is actually represented by this part, while the right side, we had to increase it. You had the laser on the top and the detector on the bottom, but now we actually need a 6 centimeter telescope and a much larger beam expander. And the reason for that is the requirements have increased. We need to go, the goal requirement is to go from 100 meters up to 20 kilometers, and the accuracy needs to be 10 centimeters at the longest distance. Actually, we can do much better than that with the time of flight we have incorporated in the current design, and the frequency repetition rate is something between 1 Hz and 10 Hz, depending on the distance from the asteroids. On the right side, I have a history of topography systems which are developed by NASA. You see they had flown MOLA in Mars. They have also launched for the ISAT-1 and ISAT-2 for Earth, and as well as the Mercury Laser Altimeter MLA. With respect to this altimeter, ESA is also flying a mission, Baby Colombo, which is going to be in Mars in a few years, and I think in 5 years from now. No, sorry, Mars. I mean Mercury, and it contains Bella, which is a LIDAR altimetry, which will provide better performance in mapping the Mercury surface, as well as they had the LOLA for the Lunar Orbiter Laser Altimeter. In conjunction to this, we have biomass instruments, and this here you see on the right side is the JEDI, which is also mounted in the ISS, but also JAXA is developing a system, MOLA, but we don't know yet if it's going to be launched and at what time, because they had certain difficulties with the thermomechanical testing. In conjunction to the previous field, we have the greenhouse and trace gases. These were already mentioned by Adolfo. We have methane and CO2, which are quite critical, and we would like to be able to measure from space. On the right side, you see a joint CNES DLR mission, which is a Merlin IPDA LIDAR, which is planning to measure with an IPDA technology the methane concentrations from space. The laser development is from ILT Fraunhofen. I think we have some people in the meeting today which have worked on this, or they are working currently on this. I can give you more information. And it's based on the Full as Future Laser activity, ESA activity. You see, we're talking about a massive instrument which is over 140 kilos and quite heavy demand in power consumption. This is using an on-off wavelength, so you fire on pulse on the absorption of the methane one close by, but not in the absorption area. And it has a PRF practically of 10 Hz because the one is the on, 10 Hz are on the on and 10 Hz are on the off wavelength for the system. On the right side, you see two ESA proposed activities. The one was the A-scope, which was a concept for measuring CO2 from space. But sadly, due to low maturity of the technologies at that time that was proposed, it was not selected. And similarly was for the water vapor Wales mission. Coming to the instrument, I was involved and I've been working the last 14 years. This is the artistic, on the left you see the artistic representation of the athlete of the EarthCare mission, and in the center of the EarthCare platform, you see the athlete high spectral resolution LIDAR, which will provide evidence in the aerosol cloud interaction, and hopefully will give its impact in the climatology. And this is very critical because we will be able to have solid proof of the global warming or not global warming of the atmosphere, and then there will be no possibility for anybody to discuss theoretics by flying these instruments in space. Actually, it's not a single instrument mission. This is very critical because you cannot do everything only with one LIDAR. We combine 4 different instruments, 2 active, 2 passive. So we have the HSRL LIDAR, which is athlete at 355 nanometers, and then we have a W-band Doppler radar and 2 passive instruments, an MSI, multispectral imager, and the broadband radiometer. And it is actually the synergy of those 4 instruments which is giving you in the end the needed information on the cloud, the precipitation, radiative flux profiles, and aerosols and cloud interactions. If we look specifically in the high spectral resolution LIDAR, you see it's a high power system. It has the master oscillator pump amplifier configuration. We still use neodymium YAG. It's also the most accepted technology for us at the moment. We produce the first 1 micron to 64 nanometers from the neodymium YAG, and then we have second harmonic and third harmonic generation to convert it down to the 355 nanometers. We have a pulse repetition of around 50 Hertz, full duty cycle, and very good M square. And you see the rest of the information on the right side. So this is a cloud aerosol HSRL instrument. What we actually do is similar to what Adolfo discussed earlier. We have 3 main products. We have the molecular backscatter, which is the Rayleigh, and then we have the cloud aerosol particle returns with both the co- and cross-polarized components, because we use Faber-Perot etalon to separate the Rayleigh from the ME, but then we use also polarizers to get the co- and the cross-polarized components of the backscattering of the clouds. It's really critical to mention that the difficulty on this technology is not specifically on the receiving side, which is also quite hard, but it's predominantly in the emission, because you need to have a very stable laser source, which I will explain later why it's so tricky and critical. And it has to be seeded. Another mission that we have in ESA and the need is the winds, because this is an instrument that is EOLOS with a Aladdin high spectral resolution Doppler wind shift LIDAR, which has been flown since 22nd of August 2018. This has a lifespan of 3 years, but we'll be able to push it further. And its objective is, by using this instrument, we will be able to have almost safe prediction of weather forecast, 7-day weather forecast, and better understanding of the atmospheric dynamics and the climate processes. It's an explorer mission, which means that it's a demonstrator of technology, because this is the most complex and most advanced LIDAR system ever launched in space. And it took quite some time to develop, and I will have a couple of slides on its development later on to give you an example of the difficulties of maturing the technology. Sadly, we didn't follow the NASA approach on this aspect in ESA, which is go with a very basic, simple design, but we tried the most difficult and complex thing you can imagine, and practically we put the cart in front of the horses and try to mature the technology during the mission development, which is, it proved to be obviously the wrong way to do it. We're talking of a single instrument mission, which is quite big, as you can see on the right side. And then you see again the same principle that we split with the Fabry-Perot, the Rayleigh, and the mid channels. And we don't use PMTs for this type of applications in space. We use ACCDs. And now I move to a little bit more compact designs of LIDARs. Up to now, we were talking about 200, 300, 400 kilo instruments, which would occupy a big mission. But now we're moving to much smaller size. This is the first category. It's for entry, descent, precision landing LIDARs. These are targeting missions to the moon, to Mars, or asteroid landing. And then you have on the left, you see the pilot developed by MDA UK. This is a demonstration model of pilot. This is a scanning instrument. The typical parameters for entry, descent, precision landing LIDARs is the mass should be around hopefully less than 8 kilos, volume less than 10 liters, and the power we try to keep it less than 50 watt. The criticalities on this is the electronics to be rad hard to 100 kilorad at least, and then we need them to be able to give us a very good resolution for up to 1.5 kilometers for having a good imaging of the landing terrain, but also be able to have precision positioning when we get down to 100 meters of a few millimeter accuracies. The difficulties also lie on these systems have quite broad field of view because they're scanning, and I will explain a little bit later what the differences between the two categories of scanning and flash systems. They need to have quite broad operational temperature operational ranges, and the specific for the specific instruments we were supposed to start the manufacturing this year for the flight model, but it's going to be the manufacturing will be launched next year. Another category, which is for hazard avoidance, rendezvous and docking a rover, and for the LIDAR, rover LIDAR systems, is a much more compact, much smaller system. We need it to be on average 2 kilos and consumption not 50, 60 watt, but down to a few watt, preferably 5, 6 watt. What you see now here is courtesy from CSEM from Switzerland, is their protoflight mounted in ISS, and this is the visual-based VBN navigation. The size and volume of this is capable of being mounted also in CubeSats, so we are having activities targeting to convert this thing to a CubeSat instrument. In the center, you see 3 photos. This is the instrument I'm referring, the VBN. On the top, you see this had a camera and a LIDAR system. So this is a photo from the camera of the objective, which was another CubeSat flying nearby ISS. Actually, it was released from the ISS. And then you see on the right side the LIDAR measurement. And it's quite interesting to look at the left side where we have the solar panels that, because they absorb a lot, you get less signal coming back, while on the top part, which was quite reflective, you have more, much stronger signal than in other areas. Another system that we have already deployed, that was the Genoptronic RVS. It flew with ATV5, and it's also a scanning system, but that is also a little bit larger in volume and dimensions. It's more similar to the pilot instrument. And one more domain that we try to promote these instruments and their potentials and uses. This is that it can do more than one things, more than one jobs. For example, we were trying to, during the AIM mission, we're trying to push this MyLast64 design from, again, CSEM, which is a scanning system at this time, because it would make it have a dual functionality. On one side, you could use it for doing the mapping of the asteroid and altimetry and all those nice things. You can create nice images of the asteroid, but then we would turn the platform and use the same instrument as a deep space optical link. So you would not need to have antennas on your spacecraft, and this could be used for transferring the data from the platform to Earth. The difference between this system and the previous ones is that, as you can see in this photo, what we typically do with the previous systems is we scan, and then we have two mirrors moving, and then we get a very quick representation of the area of interest. With this technology, we take we emit a couple of pulses, and then we take the return. We sum the return, and we get it's like a flash camera photography. So they're called flash LIDAR systems. The benefit is that it's much faster, and it covers much better the whole region of interest. The biggest drawback of this system is that it's not easy to regulate the field of view, which you can easily do with a scanning system. There are solutions to this. For example, as you can see on the right image, we have a different beam expanders. We can mount different beam expanders for the laser, and then you can have more options for the field of view in the system. Now I'm coming back to Earth, and why do I do this is because all those systems that we are developing or we're planning to develop need to have what we call CAL-VAL, calibration validation campaigns, to make sure that they're working right. And we need data in advance to make sure that to get an idea of what we expect to see. And in order to do this, we need ground stations and ground systems validated to be able to give good results. All those years we had in Europe we have the Actris network, which is providing excellent data because they're calibrated and giving good results. And on this domain, we actually have we are leading with respect to LIDAR measurements with respect to our competition in outside Europe. And here what you see is the ESA mobile Raman LIDAR, which was actually first developed by Enrico Armadillo, who is also attending this meeting today. And you see a photo on the left, the first photo on the left. This is from a campaign we did in 2014 in Finokaya in Crete, where we had both the ESA mobile Raman, the older ESA mobile Raman instrument, and next to the Poly XT, you see the signal is much weaker in our system because we have a much larger telescope, so we have to reduce. At that time, we had a 0.5 meter telescope, diameter telescope, and we had to downrate our laser to 50-60% in order to be able to not saturate our receiving side. And underneath, you see the profile we got this at that time from at that period of time, where you can see we can correlate it with an overpass from the Calypso mission, and then you see at the bottom part we had red, which is corresponding to 3, which it's a polluted continental, and 2, which is dust, which is very common in Crete. We get a lot of Sahara dust effects, and also have a high altitude dust. And you see we actually were able to capture this dust event very well, matching excellently the Calypso data. And we have this instrument took part in many campaigns, starting from 2010. We had every year almost campaign, and now it has been updated to a much more complex instrument. And then quickly you can see here the channels that we have. We have 3 elastic channels at 355, 532, and 1 micron, 3 Raman channels at 387, 408, and 607. 2 depolarization channels at 355 and 532, and we also plan to introduce a fluorescent channel at 450 nanometers next year. some photos also from Ivona. At the moment, it's in Poland, doing campaigns in Poland and Germany. You see some photos of the instrument. And this is some data I just received this morning. I asked Ivona and she sent me some data of the Immoral LIDAR at 532, 1 micron. And now I go quickly to the LIDAR architecture, assembly architecture of the system and its subsystems. I'm going to focus now on the big size LIDARs for this slide. You can see here the ALTER-ETSIT building block diagram. Everything starts with the ACDM, which is providing the control and the energy to the system. And then you have the transmitter TLE, transmitter laser electronics, which are regulating two things. Apart from the laser head, which is the RLH, this is the reference, the CEDAR, the reference laser head. It's not a trivial component. Actually, it's an extremely complex and expensive part of the instrument. We're talking about a 7-digit component. On ground, you can buy these things from Quantel for 30, 40K, but for space, these are cost over $1 million each. And then you have the beam steering mechanism, and I will explain later on why we need this. It's actually in order to it's collaborating with a co-alignment sensor at the receiving side in order to make sure and ensure that the beam is always returning back to the right position in our telescope. But then you have the two power laser heads, because in space we need redundancy to ensure the lifetime requirements, and emission baffles to expand the beams, because our target is not anymore in a few meters from the platform from the spacecraft, but it's actually 300 kilometers down. And then in our case, we need an emission baffle, which was an engineering approach to mitigate the vacuum interaction of our window, which is causing contamination on the surface, I'll explain. At the receiving side, we have the baffle again for contamination purposes, the big receiving telescope, and a series of filters in order to be able to separate 3 channels, the ME, copolar, cross-polar, and the Rayleigh channels. After the separation, you can use fiber couplers in order to transfer the signal from the free space via fibers to the right position in the detectors, and then we measure the 3 channels. I'm not going to go on details with the controlling data management unit or thermal control electronics, because these are things you find also in a typical space, in every space mission, and it's not specific for LIDAR instruments. Now, when we talk about LIDAR, space LIDAR technologies, I'm responsible for the harmonization dossier of the European Space Agency for the development of technologies in ESA, and this is one of the most complex and diverse domains you can imagine. If you have a look on the right side, you see a poster of the different elements and technologies needed to be able to build a space LIDAR instrument. It is considered by far the most complex instruments we launch in space at the moment. Aladdin and ALTER-ETSIT, the lasers are possibly the most complex commercial, not commercial, but non-military instruments we have launched in space. If we look below a chart, you see the vast need for different type of technologies that we have, and this is not from ESA. This is the S-Story presentation from 2 years ago in the NASA roadmap, where it gives you the huge needs in LIDAR technologies that need to be matured, and you see we're still at the beginning. Most of them are, some of them are even experimental, most of them are still at the development level, and only a few can be considered space proven. The next part of the presentation, I will focus primarily on the 4 domains which I consider to be very different from ground systems, which is the high fluence optics, the thermomechanical stability, the alignment, and some lessons learned. For the high fluence optics, there we can spend at least a week discussing for this subject, because it's the most critical difference between ground systems and space systems. And it is happening because of 3 reasons. First of all, because in ground systems you can have due to damage or contamination, or for some reason you can damage your system, your mirror optics, your mirrors, you can go quickly and replace one of them, and nothing, it's not a big deal. You have a few days of non-operation, but it's done. In space, you don't have this luxury, so you have to build something that will survive 3 years and probably 5 years, which is next generation of ADMLs in space. The second thing is that you have the technologies used for ground, the E-beam for coatings, the E-beam, for example, electron beam coating technology, which is producing soft coatings, has the best LIDT, laser reduced damage threshold. But if we try to use them in space, first of all, they are more prone to contamination. Second, they get a wavelength shift because they're soft coatings. Third, their lifetime is quite bad. So we have to develop a completely different generation of optics and completely different custom-made coatings. And these mean not only a lot of increase in the cost, but also a lot of delays. Almost all our space LiDARs have been suffering from delays caused by the long lead item for space optics. Typically, we lose 6 months for everything that, for every coating batch that goes bad. It induces the mission a 6-month delay. I haven't seen so far a development of a space LiDAR instrument that didn't have at least once or twice a delay of 6 months because of a bad coating batch. And I present here a large list of mitigation actions you can take in order to be able to reduce these risks, but it's always a troublesome situation. On top of that, the last part is the coating inspection qualification. There is an ISO 9211, which gives you a huge list of things you need to test, and not only cosmetic issues. LIDT, there's a big discussion how you do LIDT. SON1, which is the ISO standard, is good enough or not. It's proven that it's not. You need to do raster scanning also. You need to be able to do an endurance test. Also, you have to check for humidity, vacuum exposure, thermal cycling, radiation exposure, cleaning, solvent compatibility, adhesion, endurance, aging. Everything is critical with these coatings when you try to put them in space. And on top of that, you need to be able to repeat all those steps and processes for the diode stacks which you have to develop, because all the space LiDARs, in the past we had flash lamp LiDAR systems for ground. Now, even for the ground, we all moved to the diode stack systems, but in space we started from these, and we always need the diodes for space LiDAR instruments. We also need the high quality active lasing mediums, Q-switch crystals, harmonic crystals, detectors, optical isolators, fiber pigtails, pressure transducers. All these things are very critical components with also long lead item for space applications. And of course, we have the ITAR constraints for many of those components. For example, for the athlete TXA, we have 34 instruments which are ITAR related. And to give you how difficult it is to build a space LiDAR, due to optics, primarily due to optics, you see here the evolution, which is, it looks funny, but in reality, it's sad that the first test we did in an EQM for the Aladdin power laser head, it didn't last more than a few minutes, and we had to go in 2 years later in the first EM to switch it on, and after 4 days it was complete due to laser-induced contamination. So you see how many failures we had until we were able in 2016 to reach 160 days of operation. Every time we were trying something, there were different issues that we had to tackle. And the most critical one of those was actually the what we call LIC, laser-induced contamination. This is something which is happening in Earth as well, but not as badly and as much as we have it in space, because with the microgravitational profile in space, you don't have the gravity keeping contamination on the ground. And this is what they call LIDT bestiary, where we have the lifetime of failures from 2004 until 2014 for the high fluorescence optics of Aladdin. And you see, starting from piezo, mirror damages, isolator, we had tiger teams one after the other trying to find solutions. Whatever was the cause of the failures. Was it too much power, or was it the contamination? And you see, these things didn't stop, and actually they continued after 2014, because we continued also with the ALTER-ETSIT instrument. We had a dozen situations like this also for the ALTER-ETSIT instrument. The next big difference between ground systems and spaceborne instruments and technologies that need to be carefully selected and developed is the thermomechanical stress that you get on your instrument. On ground, it's more or less easy to regulate the temperature of operation. Even for mobile systems, you buy high top-end air conditioning where you operate your LIDAR, you switch it on and you know that the temperature during your tests will be vary from 1 or 2 Celsius maximum. So you're pretty well. But when you're rotating around Earth, for example, you go from minus 35 to plus 55 in a few minutes period. So there's a constant thermal cycling of your instrument. And then if you look closely, you see the evolution of the master oscillator, which is something that needs to be extremely stable, especially for a HSRL instrument, from the EOLOS first master oscillator to the first generation of the ALTER-ETSIT instrument to the second to the last and second generation of the ALTER-ETSIT instrument. And you can see we have more isostatic mounts, more elements now are mounted on isostatically on a master oscillator plate. Those master oscillator in-bar plate, it's much thicker now and ensures the stability. And of course, we make sure that we don't have any heating sources left and right from the master oscillator. The last tests we did with this type of architecture were very successful, and we were performing like clockwise was the report we got from Centre Spatial de Liège when we tested this, where they also did in the past the tests for EOLOS, and they had a good understanding between the difference of the two. On the top, you see a good example of what happens due to thermomechanical stability. You see the infrared, the beam is moving around because of not isostatically mount master oscillator, and you have a deterioration of the power in the infrared, which results in a deterioration of the power in the UV. The good news is that we have procedures we can increase again the power in the infrared and stabilize. On top of that, we have 2 laser heads, which ensure that we can go with good power for at least the lifetime of the mission, which is 3 years. So we expect EOLOS will continue to perform as required for at least a year and a half more until its consumables are gone. Last thing with respect to technologies is actually a decision point. And for that, it depends also, this is something that depends on what type of LIDAR you have. Do you have a large size LIDAR or a small size LIDAR? If you want to have a monostatic or bistatic design. And here you have 2 options. The first one is a monostatic design. This is the in the center, you see this is the design of EOLOS, which is flying at the moment. And the big criticality of this is that you have too many elements in vacuum. So you have to have follow an extreme cleanliness procedure, not only on your instrument, but the entire platform has to follow these requirements, which are extremely difficult to meet. On the other side, to simplify the procedures, you can choose to use a bistatic design where you emit through a baffle from one side and then you receive a different side. But then you have to make sure at every time, this is the Earth Care approach, and this is also the Calypso approach, and this is also the ISAT approach. But then you have to make sure that your emission is always aligned to the reception, and for that we use the beam steering mechanism and the co-alignment sensor you see on the right. So there are solutions for this. It's expensive and quite complex, but at least we know that there are ways to tackle the problem. And summarizing a little bit the lessons learned is that I can give you on the right you see the NASA approach, and on the left you see some of the ESA lessons learned. On the left, starting from our lessons learned, is do not assume that the competence remains in previous suppliers, and that we found out the hard way in coatings. When we moved from the Aladdin mission to the EOLOS mission, we got duplication of the coatings we got from for the Aladdin, but the results we got from the developer were horrible. And it's simple. The magnetosputtering technology used, it's an art in the coatings, and the operator who was there building the coatings for Aladdin had left. The guy who took over was not as competent probably, and the results were really bad. Second example is that we assume that heritage is happening because we have another mission that hasn't flown yet, but in reality you have to make sure that it has flown, and not only flown, but it has to flown in the exact same conditions you are flying, if you want to call it a heritage. Third point is double check instrument and interfaces of mission profiles, because if it has flown around the Earth, maybe your radiation profile is not as good if you want to use it to go to Mars, or go to Jupiter, for example, and then you have to follow different delta validation of your techniques and the components. Two more points for this is that we should always try to develop the technologies, select mature technologies as much as possible in advance, or else you end up with a ALOS situation where it takes much longer and more costly to develop during the mission. And if we could look at the left side, this is the Calypso lessons, on the right side, the Calypso lessons learned and applied to the ISET 2. And it's funny because the last one is start flight electronics design as early as possible, according to Floyd Hovis, my friend, who presented this in Paris. Sadly, they didn't, although they had this as a lesson learned because the electronics caused delays in Calypso. Again, the reason that the ISAT was delayed was primarily the development of the electronics. And some conclusions is that although we have the very slow start in Europe due to the delays in the ALOS mission, and they were reluctant in ESA to select another LIDAR mission, everybody was saying, oh, but ALOS is suffering. Nowadays, we see more and more possibilities, and more missions are coming up for LIDAR instruments in space. And the rest you can see here. I think we should save some time for questions now. Thank you. One last point, I'm putting 94 seconds of light. What I mean with this is that during the lifetime of operation of ALOS, the lifetime, the amount of light, the duration of light coming out of the instrument would be only 94 seconds. But imagine how many things you can accomplish with these 94 seconds of light. Thank you.